So chemical engineering at UCL. So first of all, most important thing, okay, that I would like really to clarify is really trying to explain what chemical engineering is. Okay, if you look at this slide, okay, as you can see, you can have things for your everyday life, basically everything from toothpaste to fuels, if you want, to chemicals, also to things that you really use really in your life, glasses, okay? So what do these things have in common, okay? The answer is pretty simple. All these things could not exist without chemical engineering, okay? So, but let's give really a formal definition, if you want, of chemical engineering, okay? So chemical or process engineering is a discipline studying how to change raw materials into useful products, okay? These products that you really use in your everyday life. Not only that, we want to do these, okay, in a safe and cost-effective way, okay? Remember, so chemical processes, we want to design them in such a way that they can be safe and cost-effective, okay? So chemical engineers understand how to change, okay, the chemical, but also the physical state of a substance, okay, to create anything from foods to fuels, okay, all these things. So both chemical, if you want, and the physical state. So which means that we don't only focus on the chemical transformation, on the chemistry, okay? We focus on that, but also on the physical transformation of a substance. So for example, in chemical processes, we can have multiple phases, okay, liquid, gas, okay, solid, okay, we can have mixtures, okay, we can have substances passing from very, very high temperature, okay, to very, very low, okay. So things that are very far, if you want, from the lab, that a chemist, if you want, might usually work. So really the difference between chemistry and chemical engineering, and this is really a key point, okay, is that the chemist usually tends to focus on the chemical transformation, okay, and they develop novel materials and processes, analyzing substances, measuring the characteristic and physical properties of these substances, okay. Chemical engineers really focus on turning these transformations and discoveries into products that are really physically attainable, okay. And most importantly, we chemical engineers are not particularly interested on producing 1 gram of a substance, okay. We are looking to the production, okay, full production process, okay. So the process at the manufacturing scale, if you want, okay. So really, we are looking to chemical plants where you can produce tons of a specific component, okay, or of a mixture, okay. So really, the other thing is we really focus on making these products for profit, okay, on a scale that is accessible to the many. Because as we said, these are the products that we use in our everyday life, okay. So that's the quantity is very important, okay. So what do chemical engineers do? So there are some things that are in common with other engineering disciplines, okay. So really the attitude to the design of projects, of engineering projects, if you want, that are, if you want, shared with other engineering disciplines like civil, mechanical, electrical, or electronic engineering, okay. So, and also when you design a complex process, you need to understand that there is an interaction with all these other disciplines, okay. And then there are aspects that are related to pure science, really. So like chemistry, maths, and physics, okay. So we are very much, okay, into the realm of merging chemistry and math, okay, and with a bit of physics, okay, in chemical engineering. So this is really what chemical engineering is. And then last thing, but last but not least, okay, we look really at the business side of things. So finance and management are very important because, as I said, we want really to design cost-effective chemical processes. All these things are really related to chemical engineering. You can be actually the guy working as a chemical engineer with a fancy helmet here, okay, working actually in a chemical plant, okay, as a process engineer, or you could be like this young girl working in the lab, okay, maybe at transformations at the level that at a later stage can be transferred to the production side, the chemical plant, okay, or you can be a little bit like myself, mostly working with simulation, okay, and software tools in order to optimize chemical processes and represent chemical processes in a very, very detailed and reliable way, okay. And then there are questions related to quality control also in all these transformations that are very, very important. So chemical engineers are involved in design, modification, and operation of chemical processes, okay, to produce a large variety of products and also to work across a very large variety of sectors. So you can work, for example, in food and drink, in pharma, okay, in oil and gas, or in biotechnology, in water treatment, okay. So in all these really sectors, chemical engineers really play a crucial role, okay, in designing really the operations, the processes, okay, and in order to optimize them. So they're really, really key, okay, on this. And there is another aspect that is very, very important, okay, which is the fact that as chemical engineers, you study transformations across a very large variety of scales. So you might work at the level of the molecule, okay, or cluster of molecules. So for example, trying to understand how molecules react on a catalytic surface, okay, and we will see that later. Or you could work at the level of particles, okay, so how to actually synthesize particles, for example, for pharma applications, okay. Or you might work at the level of the units. So in a chemical plant, you have reactors, you have separators. We need to design these units, okay, and we need to be sure that they can operate in the most reliable and satisfactory way, okay. So we need to be sure that we design them carefully and that we can really understand all the complex aspects related to these units, okay. And then when you take all these units together, you design the chemical plant, okay. So we can also operate at the level of the plant, but we can also go up the scale, okay, again, and trying to manage, for example, all the refineries in a geographical region, okay. So how these refineries interact to each other, okay. So, and this is a question of, if you want, supply chain management, which is again chemical engineering, okay. So pretty much all these scales, okay, are really used in the investigation of phenomena in chemical engineering. So this is an example, okay, of a multi-scale approach, okay. So from the molecular scale, okay, to the actual plant. For example, here you are looking at the simulation. You can see these things moving. These are the molecules, okay, reacting on a catalytic surface. A catalyst, okay, is a substance basically facilitating, okay, the chemical reaction. So as a chemical engineer, you need to understand how these molecules will attach to the surface, okay. These are studies at the molecular scale, molecular simulation, okay. But then you need to link this scale to the simulation of the actual reactor, okay. You can optimize the operating conditions of these reactors. So you link the molecular scale with the unit scale. You need to validate these models, okay, that you develop at the reactor scales, and you execute experiments in order to do that. And this might be done at the level of the lab, okay. At the lab, you have a scale which is not really, might be very, very far from the actual chemical plant, okay. So what you do is you need to do the so-called scale up, okay, of the process to reach the pilot plant really kind of reality, if you want, to match really these scale. Okay, so we have pilot plants, okay, which are plants in the middle between the lab scale, okay, and the plant scale. And these are very important because they will tell us how we can manage conditions and manage the process at a scale which is closer to the one of the actual plant. Okay? So this is basically to move from the molecular scale, okay, to the plant scale. Multi-scale approach, this is 100% chemical engineering. This is not chemistry, okay? This is chemical engineering. Okay? So what is unique at UCL? What are we doing it differently, if we want? Okay. So a little bit of, let's say, information about UCL. UCL is one of the most important universities in the UK, okay, ranked 8th worldwide. And we have basically all the faculties at UCL. And it is a very inclusive university in terms of ethos. As you can see here, this is one of the fathers, okay, of UCL, the philosopher Jeremy Bentham, okay. And this is the Department of Chemical Engineering. This is the engineering building, Roberts building. So you have not only chemical engineering, you have also the other, basically, engineering disciplines. Well, some of them, okay. In the engineering, okay, in the Faculty of Engineering, we have basically all the engineering disciplines, okay. So we have also biochemical and chemical engineering in particular are two different departments. This is actually unique in the UK because usually they are grouped together. The reason why at UCL they're not grouped together is that in that case we would have a very, very big department, okay? So incredibly big. So from the point of view of management and ensuring the quality, it has been decided to split, okay, into two different things. Chemical engineering is focusing on really chemical processes, okay? Biochemical engineering is focusing more on processes where you use biochemical entities or bioprocesses, okay? UCL Chemical Engineering is one of the most prestigious departments in the UK. It's ranked 4th, okay, in chemical engineering and 18th worldwide. So very, very good ranking. We also have a very, very big project going on at UCL East in the Stratford area, where we are actually building a lot of new facilities, including, for example, new pilot plants, okay, mostly for research, but also for teaching, okay, purposes. So this is really in the Olympic Park area, okay, and this is a very big development. The campus is based currently in the Bloomsbury area, okay, of London, a very, very central part of London, and very close to all the amenities of the city. In terms of chemical engineering programs, we are offering a BEng in chemical engineering and an MEng in chemical engineering. And then we have a number of potential routes, okay. You can have a chemical engineering MEng with study abroad, with biochemical, with chemistry, and with engineering mathematics. Also, we have a number of MSc programs, okay. All our programs are accredited IChemE, okay, which is basically the most important institution of chemical engineering in the UK and international, I would say. This means that you have a preferential pathways when you attend these accredited courses to engineering chartership, really to become really professionally a chemical engineer. In terms of numbers, we have more or less 500 students between year 1 and year 4. We have around 80 postgraduate students. We are 150 research staff and students and 27 members of the academic staff. We also have 10 teaching fellows, which the difference between teaching fellows and academic staff is that the teaching fellows only teach, okay? While the academic staff, well, like myself, we both do research and teaching, okay? So the other important thing is that we got awarded the Athena Swan Silver Award for our commitment on equality of genders, okay, in in the department. So we're very proud to say that we have basically around 35% of female students actually studying with us, which is a very, very high percentage compared to other engineering departments in the UK. Okay. About the program routes, you can have a 3-year BEng, okay, in chemical engineering. You can spend your 3rd year in industry, okay, we will see that, and then end up with a 4-year BEng in chemical engineering, or you can go for a standard MEng route, okay. As you can see, the first 3 years between the BEng and the MEng are in common. So you have exactly the same modules. The other option that you can have is you can spend your 4th year abroad in another university, or you can switch to another route like biochemical, chemistry, or engineering mathematics. Or you can spend your 4th year in industry, and in that case, you would end up with a 5-year program, a MEng program in chemical engineering. Okay, so you could, in theory, also have the year in industry and the year abroad. Again, you will have your final year, okay, abroad in another university. Is also possible. What are these universities? So you have a number of universities in the US, okay, including MIT, Purdue, Wisconsin, Georgia Tech, and Columbia, and others. The important thing here to say is that our study abroad year is really part of the MEng degree. So it is fully accredited ICME, okay? So this is very important because we need to be sure that when you go abroad to the other institution, the quality, okay, is ensured and the standard, okay, are basically the same or higher than the ones that you have at UCL, okay. This is very important. And then the other thing is we have other universities in Australia, like Sydney or Melbourne, okay. We have many other universities in Europe, okay, including France, Netherlands, Italy, okay, actually where I come from, University of Padua, and Germany, Greece, and Spain, okay. So quite a lot of universities. About the year in industry, we have an industrial advisory board, which is actually helping us to shape our teaching program. And they also, industry provides guidance with year in industry, okay, on finding placement, and also they help us organizing career events. They also are involved in events and workshops to basically explain and elucidate how to write a CV and how to shape your interview skills. And some of the employers are GSK, ExxonMobil, Nestle, Air Products, and more, okay? So we have very, very much, a very strong link with industry. And this is for both teaching and research, really. Okay. So let's take a look to the program, okay? This is actually a program that, let's say, we have normally, okay? As you know, in this year of COVID, the program has slightly changed, okay, because of some readjustment of the modules, but the usual, okay, program that we have is this, okay. As you can see, this is color coded, so you have modules in red, in green, in blue, okay, and some in orange, okay. So the modules in red are the so-called integrated engineering program modules, okay. These are shared with other engineering disciplines. So you can see engineering challenges, design and professional skills, mathematical modeling and analysis. Math is very important in chemical engineering, okay? So in the first year, first term, you have a first introduction to chemical engineering. As you can see, the green modules are the core chemical engineering modules, okay? So you have a first introduction in the first term. Second term, you have transfer phenomena. Transfer phenomena is basically how can we describe and study the behavior of fluids, okay, in chemical plants or even in pipelines. So we need really to understand this very, very well. Thermodynamics, very simply, okay, in chemical engineering, we have different phases. Okay? We have gas, liquid, solid, but also we have mixtures. We need to be sure that we understand the properties, okay, physical chemistry, which is chemistry, okay. Computational modeling and analysis. Usually the mathematical models that we have in chemical engineering are quite complex, okay? So you cannot really solve them analytically. You need to have some software and numerical tools in order to solve them. Then year 2, as you can see, we have design and professional skill 2, mathematical modeling and analysis 2, okay? And these are, again, integrated engineering program that I will explain later. We have a full module on experimentation, as you can see, engineering experimentation, and elements of experimentation in modules in the second and third year. Okay? As you can see, the blue corner that you can have here. Then you have heat transfer. So as we said, we change the physical state of a substance or of a mixture, not only the chemical. Okay? So temperature, pressure, we need to be sure that we understand how to really change this in a process, in a chemical process and in a chemical plant. Separation processes, how do we separate the components from a mixture? So for example, we have some so-called unit operations, distillation, extraction, absorption, adsorption, and more, okay? So you can have different units actually operating this separation. You have one in the second year, and you have two in the second term of the second year. You have a first module on chemical reaction engineering here. So how to design a chemical reactor, okay? This is very important. You have a second part in year 3, and this is basically dealing with catalytic processes, okay? So design of reactors where you have catalysts involved. Then we have chemical reaction engineering 1 and 2. We have particulate same systems and separation processes. How to create a tablet, for example. Crystallization processes. Processes that are relevant in pharma applications, if you want. Process dynamics and control, which is the module I teach in the third year. So how can we be sure that we can maintain a specific, let's say, target quality, okay, in a product, even if we have disturbances? We need to design a proper control system. And also we need to reject the disturbances that might affect, okay, plant or a system in general. And then we have transfer phenomena too, okay, fluid dynamics of more complicated systems. Also safety and loss prevention. This is very important because we want to design chemical processes that are really, really cost effective, but most importantly, safe. Okay. You have modules in orange, as you can see here, from process design principles, second year, process design project in third year, and process systems modeling and design in the fourth year. These are modules where you are asked to design a chemical process. You start from more simple, okay, basic design. Then in the third year, you will explore really the design of a chemical process very, very much in detail. This is a 1 year long process design project, okay, involving most of the academics of the department. Okay? So we have experts in reaction engineering, experts in process dynamics and control, experts in safety, okay, and so on. Okay? And they all support the students in the delicate and intricate decisions to really take during the process design. And then you have in the fourth year, this is a MENG route, you have the research project, okay? And this is done in collaboration with one of the academics. As you can see, you also have a design module in the fourth year. This is process systems modeling design that I teach, okay? This is on the design of a full chemical plant, okay? But where the focus now is to model each single unit very, very much in detail and to optimize, okay, a chemical plant. When I say model, I mean really mathematical modeling, okay? So produce custom models and also use advanced simulation tools for that, okay? So that's really my key area of expertise. And as you can see, you also have a number of electives here. Let's look. In the fourth year, you have modules that you can actually choose, 5 of them, okay? Between chemical engineering related modules, but extra modules that you might really like more, that might be like energy systems, electrochemistry, They might be related to nature-inspired chemical engineering, that we are very much at the forefront on this, because we have a center for nature-inspired chemical engineering in the department. Or you could also go for non-chemical engineering related electives. Let's say you have an interest in law, okay, management, okay, project management, or even to learn additional languages, okay. You can actually add these extra elective modules to the program. So the integrated engineering program, what is this IEP? This is a very advanced program where you have basically a cross-disciplinary platform where the students really tackle real-world problems working with other engineering disciplines, okay? And they work together using research and to develop technical and team working skills. And these are skills required not only by academia, but also by industry. So very, very important. So key aspects of this IEP: challenges, scenarios, how to change the world, and minors. Let's take a look to some of them. Challenges are two major 5-week integrated design challenges. These are year 1, term 1, so very first beginning of your study at UCL. You work together with other engineering disciplines, students from other really departments, maybe electrical, civil, okay, mechanical, to really formulate, for example, design and verify a strategy for the production of a vaccine. As you can see, this is very much relevant, okay, to what we are living today with COVID, okay. So can we actually work together to develop a vaccine? In this case, it's a vaccine to combat a tuberculosis pandemic in Africa, okay. But still, the kind of tools and methods that you're using are relevant, okay, to the world we are living, okay. You have some interaction with other engineering disciplines, because together with the transformation, which is a bioprocess where you work together with biochemical, if you want, engineering, you need to work together with civil, okay, mechanical engineering, because you have also the possibility to have parts in movement, and also to electrical engineering, because you need to control, for example, and monitor this process. This is really a bioprocess where you have some microorganism actually operating this transformation. So the students really work in groups together with students of other engineering disciplines to tackle this very important and key problem. And then you have, you know, scenarios here, and as you can see, and how to change the world, and the minors, second and third year. So the scenarios are really 6 one-week-long disciplinary design challenges. They can be focused on principles, design aspects, finance, sustainability, and they really are specifically targeting your research skills, your presentation and team working skills. Again, you work together with other students, okay. Scenarios may be on chemicals, so really process plant design. They can be related to energy, for example, transportation, natural gas and liquefaction, or biofuels, okay. So, or they can be related to separation of air, or they can be other things like related to cross-sector or pharma applications. Let's see, for example, an example from pharma, okay. This case, the students were asked to really actually assess the viability of a formulation, okay, and actually creating a tablet. Okay. Tablet, you have an API, and then you have excipients. But how do we formulate this? Okay, this is very important. The students studied in the lab, okay, how to create the tablet, how to optimize the formulation, and they ended up with a technical report and also with some creative presentation. Minors. So what are these minors, IEP minors? These are 3 modules that you can pick up within a different or interdisciplinary area. Examples. So let's say that you have an interest, okay, in applied chemistry, okay, or you want to learn a little bit more about chemistry. You can pick up 3 modules, okay, related really to advanced chemistry if you want. Same can be done in other, let's say, topics, okay, environmental engineering, finance. If you really like, for example, machine learning, you can have one in intelligent systems. If you really like, let's say, programming, you can have one on programming. These ones that you can see here underlined are the most popular ones, okay, from students. Let's take a look at really applied chemistry and molecular engineering minor. If you have that minor, okay, you have this sort of background. So you have a core physical chemistry, okay, compulsory module. Then you have 3 modules for the minor in organic chemistry, and molecular engineering. Okay, these are 3 additional modules that are basically complementing a preparation which is totally chemistry oriented. Okay? Then you can have electives. Remember, in the 4th year with IMEng. So you can have, for example, environmental science, nanotechnology, okay? And you can go for a research project which is chemistry oriented. Okay? We have a lot of academics working on really fundamental chemistry, if you want. So let's take a look about the general structure of the modules that we have. So how are we teaching this? We have usually lectures and tutorials, around 30 hours over 8 to 10 weeks, with elements of experimentation and computation. So as I said, you have labs, but also you have computational elements, so use of the software. Okay. Use quite a lot the e-learning, so the Moodle platform, okay, really to communicate with students, to share the material, and also to assess, okay, the students in many cases. We also have the interaction given by the year 1 and year 2 scenarios. So when you have the scenarios, okay, basically you don't have any teaching that week. Okay, so the teaching will stop, and you will only concentrate from Monday to Friday to the scenario, on the scenarios that are really, you tackle this design challenge, if you want. Okay. Safety is also very important, and it is present in a number of modules that we are teaching, starting from year 1 and 2, with the scenarios and the design and professional skills 1 and 2. And then you are actually studying safety with a capstone design project, the 1-year-long design project I was mentioning earlier. And also you have a full module on safety and loss prevention. This is really focusing on quantitative risk assessment, okay, which is very, very important. Computation is present across the whole program, together with the most standard tools like MATLAB and Excel. We teach the use of GAMS, GPROMs, and Aspen, which are state-of-the-art software for simulation and optimization. Okay? So these are very, very important. And then we have also experimentation, one full module from the very beginning. Then we have also elements of experimentation in year 2 and year 3 in various modules. Okay. Example of a timetable. Usually students have lectures in the morning, okay, 9 to 1. And they have tutorials that can be computer tutorials or lab tutorials in the afternoon. Okay, so this is usually the sort of let's say distribution, if you want, of lectures. We use a lot the virtual learning environment, so Moodle, where we share the material, where we interact with the students, where we get a feedback from the students, and where we also mark some of the students' work. Okay. We use also quite a lot the lecture cast. Okay, particularly now that we are in this situation of pandemic, we're using a lot the recorded lectures. Okay, it looks something like that. So you have slides and the lecturer, okay, on the right. You can also see the various aspects, and this is very interesting because if the students cannot attend the actual session, okay, you can always go back on Moodle and look at the recording. Okay, so that's very important. We use a lot now with the pandemic, the remote teaching, of course, as most of the universities. We use Zoom quite a lot, this tool also for teaching, Teams for tutorials or one-to-one meetings, Moodle and LectureCast, okay, really for the availability of these lectures. In terms of statistics of our program, we have very, very good statistics because 6 months after finishing the course, 80% of the students are working, okay? 10% are doing further study, okay? It might be MSc or PhD. And also, in terms of employment, 6 months after the course, 95% of our students are in a professional or managerial job, okay? 95%. So it's a very, very high percentage. In terms of entry requirements, and you know, I'm the admissions tutor, so if you have any questions, feel free to contact me, okay? We have these entry requirements. So we are asking for A equivalent in math, chemistry, and another science subject, preferentially science-related subject. So AAA, okay, math, chemistry, third subject, preferentially science-related. We also ask for English language certification, okay, from GCSE, English language and maths a grade C or 5. For UK students, you also need to have a grade C or 5 in a foreign language. Okay, this is we require. This is UCL regulation. About this third subject, okay, this doesn't necessarily have to be science related, but it is really preferential. This is preferred. For example, you have a list of preference on the third subject. At the top, you have further math, physics, biology, okay, and then so on. These, in terms of let's say selection, might become important. And also we have the equivalent entry requirements for the IB diploma. So 38 total points with 18 points in 3 higher level subjects, including math, chemistry with no score lower than 5, and again, the third subject, okay? We have the same basically equivalent requirement in terms of GCSE, and also you need to demonstrate English language proficiency, okay? And there is a list of language certifications that are actually accepted by UCL. For UK-based students, again, we need really to have a grade C or equivalent in a modern foreign language. So this is really very important. So I think this is most of the things that I wanted to cover, okay? If you have any questions now, either you ask now or even later, okay, you can send me an email to this email address. Also, be sure that you follow us in the various social media that we have, so including YouTube, Facebook, and Twitter, okay? I think Mark also has some links about taster lectures that you can look into, so that you discover a little bit more about the research that we do, okay, in our department and the exciting, really, things that we are doing, okay? Other than that, I mean, happy to answer any questions you might have. Thanks. So if you can use the Q&A box that you have really at the bottom, there should be like a Q&A box that you can use in case you have questions. So how has studying at UCL changed because of COVID, and are these changes likely to continue to next year? This is a good question. So I can tell you what really was changing with this pandemic. In terms of program, there was minimal changes, okay, mostly, let's say, related to the fact that, for example, lab activities are limited, okay. So this is one thing. The other thing is that most of the lectures have become really virtual, okay. And in this first term, for example, we only had several enrichment activities, which were activities, face-to-face activities, okay, with the students. But most of the lectures were done really online, okay. Is this going to continue? We don't really know exactly, because originally we planned to have, for example, only the first term, okay, online. And we said, well, the second term might be maybe open to students, okay. While now we can see that the COVID is still, cases, number of cases are still high. So the second term will still be online, okay? And we don't really know if next year things will change, okay, depending on let's say global scenarios that we could have, okay, worldwide. So it's very difficult to say if these changes will continue, okay? But what I was presenting here was really our program, okay? There is another thing also that was changing last year, okay? Well, this year actually, which was related to the assessment of the exams, if you want, okay? So the other thing is we prepared alternative assessments, okay, which were done really to be sure that we were able to examine the students with the highest possible standards, even if we were doing online. Okay, so we developed, and this was a lot of work, okay, specific ad hoc projects, okay, done in collaboration with the academics, and that the students had really to tackle during the exams. So in essence, it's very complicated if you want to give you an answer on a future that we don't really know for certain, okay? But the thing that we can easily say that we are very, very well prepared to any possible scenario, either virtual teaching or face-to-face teaching, okay? We are prepared in terms of support to students, in terms of platforms to use, and in terms of now skills, okay, that we can have to manage this sort of situations. So the second question is on, is there interviews, okay? No, we're not really interviewing the applicants. Basically, the application is based on, just based on three things, okay? So as you know, you need to submit a UCAS application, okay? The application will have your grades, okay, your personal statement among your information, okay, and also references from the school, okay. These are the three elements that we are going to look into the detail. So grades, most important thing, because if you don't have the grades, really, it's very hard to have a place at UCL. Particularly this year, where we had a big increase in the number of applicants and a big increase in the number of students, okay? We had no students, okay, below the entry requirement. So just to give you an idea, okay? And we had an increase from our target of 120 to nearly 180, okay? Just to give you an idea, first year students. Second thing is the personal statement. So you need to be sure with the personal statement that you really convey the message that you know what chemical engineering is, and that you really have passion for this, that you are committed really on studying this topic, okay, in detail. So this is something that you can do in many ways. You can use some experience that you might have, for example, visiting a company on an internship, or I don't know, on some specific reading that you went through, okay. I encourage you to look, for example, to the iChemie website. This is a very good resource, okay, if you want to learn a little bit more about chemical engineering. So what are the entry requirements for international students? So I was saying, if you have, for example, other qualifications, so either you have, if you have A levels or equivalent, all the other qualifications are based on these entry requirements. So any, let's say, different qualification that you might have, okay, this is always viewed in relationship with the AAA, okay, equivalent. So it means really you need to be very proficient in maths, chemistry, okay, and in a third subject. Okay. regardless of the specific qualification that you have. There is a huge table of equivalences, okay, because every country will have its own, okay, specific qualification. But the equivalence is done always with relationship with the A levels. Okay? This is just to be sure. The recording, I don't know about the recording, maybe Mark can help on that. What will happen with the scholarship for the undergraduate students in 2022 to 2023? Is there going to be any or not? We will have at the level of UCL scholarships, okay? And there are links, I can provide, if you can send me an email, I can send you the links for scholarship. But usually these scholarships are very specific. They might be specific for example, international students. They can be related to specific areas, okay, of studies. You need a little bit to look at it, okay? So we have, let's say, some bursaries to help students that are really in difficulty, okay? So this is also another thing that you can have. You mentioned that 95% of students are in employment after 6 months of graduation. Is the 95% in jobs in the chemical engineering area or in any type of job? This is a good question, okay? Actually, we have, let's say, a 60% of them, okay, are working in the process engineering area. Or process engineering means, you know, it might be really chemistry, it might be materials, it might be, but still in process, in the working in the actual process. Then we also have a significant amount of students, I would say around 20%, okay, that are actually working in finance and business, really in the city of London. So they might work for really big companies, financial companies, okay, and they have a very, very competitive salaries, okay. Some of my students, they actually are in they have jobs that are really, really very competitive from that point of view. Why is actually finance and business so attractive? Okay, salaries is the first reason. The second thing is that these companies are actually looking for people with analytical skills, data analysis skills, okay? And our graduates have really, they tick all these boxes, okay? And so they really find easily employment in this, also in this area. Regarding semesters, are there 2 terms in total, or is there a 3rd term for exams? Yes, so thanks for the question. So you have 3 terms, okay? Term 1, which is basically, say, October to December, okay? Then you have term 2, which is basically January to March. So they are not semester, they are trimesters, if you want. And then you have term 3, which is from April onwards, which is actually dedicated to exams. Okay, so that's really, exams are only in the 3rd term. Okay. How do the chemical engineering with XXX, let's say, differ from plain chemical engineering? So the focus is different. For example, if you have chemical engineering with mathematics, okay, you have a stronger background on math-related subjects. It might be, for example, related to numerical simulation, numerical analysis, data analysis, okay, things that are very, very appealing, okay, to a wide number of sectors. Or if you have, for example, with biochemistry, okay, route, this is really, if you really like bioprocesses, okay. So if you really like bioprocesses, you can actually go for that. And this is just to give you an idea. If you go for a chemistry route, of course, it means that you will have a background which is more solid on, for example, organic chemistry, inorganic chemistry, okay, molecular engineering, nanomaterials, okay, these things, which are also quite exciting. So is necessary any type of work experience? No, the thing is, okay, if you have some work experience, you can use this experience when you write your personal statement. And this is important, okay? Because you can convey the fact that you know how, for example, a chemical company works, okay? Or some, okay, aspects of a chemical company works. So this is really very, very important. So to answer really your question, we are not requiring any specific work experience, okay? But you can actually use somehow this experience when you write the personal statement. What about contextual offers? So we have a contextual offer, which is actually based on AAB, with B in the third subject. This is only related, okay, to students coming from disadvantaged areas, okay? So this is a scheme which is done at the level of the college called Access UCL scheme. Okay? This is really to encourage a wider participation to the higher education. Okay? And this scheme is basically very important because it's a sort of way of ensuring that applicants are freely to come to UCL regardless of their background, okay, from the point of view of really of the school, okay. So for example, schools in disadvantaged areas, they can adhere to this Access UCL scheme. Students from these areas can have this contextual offer, okay, provided that put UCL as first choice, okay, in their application. So as first choice for the application, and that they need to complete also an assessment, a very simple assessment, okay. They come at UCL. There is a day, okay, that they spend on that, and then there is a sort of simple assessment document that they need to fill, and then they get this contextual offer, AAB. B again in the third subject. So math and chemistry, they still need to be at A. Okay. Other questions? Any other questions? No questions? We still have a few minutes if you have some curiosities or even, no? No questions? Yes, so Mark has actually included a link to the tester lectures. This is quite interesting because they are covering a variety of topics, okay? And they give you an idea of all the various, if you want, facets of chemical engineering. So it's really, really nice. So what are the top things you look at in the personal statement? So first thing, okay, is, and this is the most important, okay, is that you need to convey the message that you really know what chemical engineering is. So you are applying to chemical engineering, not to chemistry, not to maths, okay, not to biochemistry, okay. So you are applying to chemical engineering, so process engineering, okay. So I went through the presentation, okay, through all these aspects because I just wanted to clarify this. Okay? So this is the most important thing. The second important thing is that I need to see that, you know, provided that you know what chemical engineering is, okay, that there is a sort that you really like, okay, that you have a sort of passion on studying topics that are related to chemical engineering, okay. So this is really, these are the most important things. If you have previous experience, okay, you can use that, but this is not strictly necessary, okay. You can rephrase your statement, okay, in such a way that you really demonstrate, for example, what that you know what a process is, okay? What a chemical process is, and what are the challenges. The other thing is you could also use really the everyday, if you want, life really to elaborate more on your statement. Okay, I don't know if you've ever asked yourself, okay, where does this thing come from? Okay, where is this mobile phone produced? Okay, so and how do we produce this component? Okay, for example. But also, this is just an example, okay? But you can always, let's say, give a practical, if you want, view of what chemical engineering is, because chemical engineering is really around us, okay? And most of the people don't know that. Hope this was clear. Other things? Other questions? I think we are more or less, yeah. I missed the start of the presentation, so I don't know if you mentioned about the percentage of women and men in the course. Does it matter when graduating as a woman to get a job in the field? So yes, I mentioned in the presentation, so we have been awarded the Athena Swan Silver Award. This is an award given really for our commitment on equality of genders, okay, in the environment. We have 35 to 38, okay, % of female students, okay, in our cohort, which is a very high, okay, percentage compared to other departments in the UK. Does it matter when graduating as a woman to get a job in the field? Well, this is really an interesting question, okay. Certainly, looking at the statistics, okay, that we have, it doesn't really make any difference, okay, being a man or a woman in this context, in terms of employability, if you want, okay. Then in general, not so sure about this, okay. So when I'm saying general, okay, situation might be different. Other questions? Well, if not, I think we can end this session. Again, feel free to contact me, okay, if you have any questions even after this virtual open day, okay? Thanks for joining again, and take care.